Hi everyone. Sorry to be missing you today. Wasn't expecting to be out, but things happen. And really, if yesterday's lesson went okay, this lesson should be just fine for you. And we do have a built-in review day tomorrow, so we'll make sure to go over any of this that you need. But until then, let's get through this stuff so you can get on to your homework here. Today we're talking about translating circular functions. Okay, yesterday we were talking about scale changes. So we were talking vertical stretches, horizontal stretches, things like that. Now we're going to be picking up these graphs and moving them around. Okay, sliding them up, down, left, right, things like that. And we do have one vocab word here to throw out, and that's phase shift. Phase shift is the magnitude of a horizontal translation of a circular function. I'm throwing this word around a lot without really telling you what I'm talking about. Circular function. All of these functions we've been talking about are circular because they're based on a circle, right? They're based on the unit circle. Really, this is the same meaning as saying that they're periodic functions, okay? And so the reason I think that periodic functions get their own name for horizontal translations, because on every other graph we just call it a horizontal translation, is because of that repetition, you can have different horizontal translations that result in the same image. And you'll see what I mean by that. But basically, like if I pull something to the right by 2 pi, or if I pull something to the right by 4 pi, it's all going to look the same because everything repeats every round of 2 pi that we go. Okay? So we call it a phase shift just because it's not unique. It's not as unique as like a horizontal translation would be. So let's get our rules and our terminology down here. Now we're talking about translation rules, and translation rules involve adding and subtracting. So it's our old friends H and K again. Okay. H, because it's affecting the X, that's going to be our horizontal shift or our phase shift. And in rule form, when we're looking at it as a rule, we can pretty much trust what's written there. So addition would move us to the right. Subtraction would move us to the left. I hope that my symbols make sense there. Okay. The K value is acting on the Y, and so that's going to represent your vertical shift. Positive values would move you up. Negative values would move you down in terms of the vertical axis. So when I look at this function, in example 1, sine of x plus 2 pi over 3, and I want to identify what the phase shift is, I need to get myself to this rule form. Remember, a lot of the times your first job will be to get the rule. And this is an equation, which means everything is backwards from what it should be. So when I write my rule, I would say x minus 2 pi over 3. And then nothing's happening to the y, which is really your p of x. There's no adding or subtracting there, so I'm just going to leave that alone. That's my rule. And so then my phase shift is really, what is this representing? And this would be moving a shift of 2 pi over 3 to the left. And I want to just illustrate this for you real quick. So I'm going to stealthily try to switch back and forth between this video and Desmos. We'll see how it goes. That's not it. There it is. Okay, and so on this graph, I'm going to graph the original y equals sine of x. And then I'm going to graph the problem from this example. Sine of x plus, oh, yep, that was the original equation, 2 pi over 3. Okay? And what you should be seeing here, and this is going to be really hard for me because I can't point to the screen, but if I look at the distance between, say, like this top red bump and this blue bump here, this really ended up getting dragged backwards by a total distance of 2 pi over 3. Okay, the distance between that negative pi over 6 that you're seeing there on the screen and pi over 2 over here, that is a horizontal distance of 2 pi over 3. Okay, and so I just took that red graph and dragged it. Well, that's not going to work, but I took that red graph and dragged it backwards, and it became the blue graph. Okay, so again, just wanted you to see visually what I was talking about is that I took all of my points and shifted them over by a value of 2 pi over 3. Okay? Okay, So back to our examples here. So this one gives me a rule, and it wants me to write it in this equation, okay? So remember, we're going to put everything into the equation backwards from how it looks in the rule. So it would end up looking like this. Y plus 2 equals sine of x minus pi, okay? And then, just like we talked about yesterday, normally we would go ahead and drag this 2 over and write it on the other side. So we would probably say y equals sine of x minus pi, okay, minus 2. So, because I would subtract it from the other side. So this is how I would leave my answer, okay? So what you've got there is a graph of the original sine function, okay? If you notice, it's got a period of 2 pi, it's got an amplitude of 1, it starts at 0, all of those things we look for the sine function. This is telling me to move pi spaces to the right and move down by 2. Okay, hopefully that makes sense in that rule. And again, notice I'm looking at the rule and not the equation, because in the equation everything is backwards. So what I'm going to do is I'm going to take each one of the kind of critical points here, and we probably only have to do kind of one full cycle's worth, and I'm going to do exactly that. So I'm going to shift this guy to the right by 1 pi, okay? And I'm going to shift it down by 2 spaces. So right now it's at 0. I'm going to move it down to -2. Okay? Now I'm going to take this point. Pi over 2, if I shift to the right by pi, that's going to go to 3 pi over 2. And then I'm going to drop that down by 2. So right now it's at +1. I'm going to go down to 0 and then go down to -1. So that would actually correspond with this point right here. Okay? Pi, this one, is going to move to the right by 1 pi. Okay, so pi would now become 2 pi. And then that drops down by 2, and that's going to take me here. I'm going to run out of space shortly, but the good thing about periodic functions is I can just turn around and go back the other way. 3 pi over 2 when I add 1 pi to that. And keep in mind your fraction rules here. If you're not sure what 3 pi over 2 plus 1 pi is, let's write that 1 pi as something over 2. So 2 pi over 2 would be equivalent to 1 pi. And so that's really going to become 5 pi over 2. Okay, whoops, I should be here. 5 pi over 2. Now, I didn't do a very nice job here because this point technically goes down below your graph, right? This point would be down here if I drop down 2 spaces, okay? But I could keep going, right? I could take this point and I could shift to the right by pi and I could shift down by 2 and I would end up with kind of one full cycle there, okay? It would really be like this is my new axis, okay? And so my graph is kind of going like that. Can't see where I'm drawing, but so that at least got me to one full cycle, and I mean I could keep doing that, right? I could keep taking each one of these points, moving it over by pi and down by 2. That would take me to this. Grab this one, move it over by pi and down by 2, and that would take me to this. Okay, this one over by pi and down by 2 would take me here, and so you could keep going and fill in the rest of this function. Okay, if you needed to complete the graph. Okay. You could also set up an XY table like we did yesterday, but this one I felt was simple enough that we could probably just work straight off of the rule. Okay, let's go to our next example here. Ooh, next example is involving a tangent graph, which we haven't used a whole lot, but we'll be fine. This is an image of tangent of x, okay? So our original tangent function has been transformed in some way, okay? And we want to know how. Well, if you look at the way this curves, okay, this is kind of that center point of the curve. All right, look, it's the same here and the same here. That's where you've got that rotational symmetry, right? So I can tell that this tangent graph hasn't been shifted up or down at all. There's no vertical shift here. But where is this point normally? Okay, think about that for a second. On the tangent function, where should this be? This should actually be here, right? That this original point would have been at the origin. The tangent function crosses at 0, 0. So judging by that point, I'm going to say that this graph got shifted to the left by, and let's see, it's half of pi over 2, so that would be pi over 4. So for my rule, I would say x minus pi over 4. And we said there was no vertical shift, right? So our y is just going to stay the same. X minus pi over 4 and y. Now, here's the thing, and this is what I was kind of talking about earlier with the phase shift. Someone else might make the argument that this was at the original origin, okay? And that I took this origin point and I shifted to the right by, let's see, what would that be? 3 pi over 4? Yeah, halfway between pi over 2 and pi, that would be 3 pi over 4 right there, okay? And so you could make the argument that your rule is actually x plus 3 pi over 4, and you would be correct, okay? There's no way of knowing from looking at this graph whether this was the original one at the origin or this one, okay? So both of those answers would work, and both of those answers would be perfectly acceptable. You could go really crazy and say, hey, I think this was the original one at the origin. I think that it shifted all the way over here, okay? And so that's what I mean by phase shifts are not unique. Okay, you can shift by different amounts and still end up with the same picture. Okay, so we wrote our rule. We didn't write our equation yet, but that's usually the easy part. I'm looking at this equation, I'm looking at this rule, and my equation's now going to look like this. Tangent of x plus pi over 4. Just make sure anything that you're trying to put with the x goes in parentheses with the x, because otherwise if it's sitting out here, it looks like maybe it belongs to the y. Okay, one more to do, and we've kind of already talked about what's happening here. This graph, if you look at it, is actually the sine function, but it would like us to write this as though it were a translation of the cosine graph. Okay, so we're pretending this is not a sine function, we're pretending this is a cosine function that has been translated. Well, let's think about what this would look like if it were the cosine function. If it were the cosine function, this bump right here would be right on the y-axis, right? This would be coming down like this and so on. Okay, I'm not going to draw the whole thing in. So I'm going to make the assertion that this point got shifted to the right by pi over 2. Okay, that this thing got shifted to the right by pi over 2. So as a rule, and again, I should have mentioned this, but there's no vertical shift here, because if you notice, my amplitude still goes up to +1 and down to -1. Okay, if this were like off-centered here, I would know that there was a vertical shift here. But my rule, I'm going to say we went to the right by pi over 2. And so for my equation, I'm going to say y equals cosine of x minus pi over 2. Okay? And again, we've talked about that sine and cosine are off by a value of pi over 2. So you could think of it as a translation. You could think about it as in a right triangle. Okay, we've hit this topic quite a few times, but this is all this question really wanted you to do. Okay, so I'd like you to give a few of these a try. Your homework is out of the textbook, section 4.8. And then when I am back tomorrow, we will talk about 4.7 and 4.8, and then we'll just kind of review everything we've done so far this week. Okay, hope you have a great day.